state Kirchhoff's first law. When you see first law, Kirchhoff only has two laws. When you see first law, is the one that has to do with currents and junctions. When the current comes to a junction, such as this, then the current have to split in two paths, right? So maybe one path here, one path here, for example. Whatever comes in has to come out. So if 5 A is in, this has to be 4 plus, for example, 1. 4 plus 1 must equal to 5. I cannot simply have current disappear or current appear. That's related to charges. So we can say that the total or sum of current into a junction is equal to the total or sum, let's say sum lah. The sum add up together of currents out of junction. This is one way of saying it. So current in equals to sum of current out. Or another version is to say the algebraic sum of current in or out of junction, whichever, equals to 0. So in that case, I will say like, oh, maybe into this nice junction, I say plus. Those that are coming out, we lose a charge, so we minus. So 5 minus 4 minus 1, 0. Okay, very good. So that's the second way of saying Kirchhoff's first law. You can say the algebraic sum. If you don't say algebraic, it's also okay. Sum of currents into junction is 0. Is 0. So for the first method, you must say total of sum though. Cannot say, oh, current into junction is current out. You mean the total current into junction. So use the first one, you must say sum. That will be B1. If you use the second method, just sum of currents, algebraic sum of currents in junction is 0. That's also one possible mark. Yeah. Now this Kirchhoff's first law, actually, where did this idea come from? This comes from idea of conservation of energy. Or no, that's the second law. Conservation of charge. You see, all this current, we so-call current, it's actually charge flowing, right? So yes, the concept behind this, why the sum of current is like that, is because the charge is preserved. Not current is preserved, charge is preserved. If the charge is here, you have to go in junction, you must come out. Imagine a traffic light, all the cars go in and then no car come out. Wow, ghost cannot. So conservation of charge is the principle, but it is not the definition. That's actually part 2 lah. Kirchhoff's first law is linked to conservation of some quantity. What is that? Charge. So the definition, unfortunately, we have to stick to the sum of currents in or out of junction. We cannot say current is preserved throughout the circuit because charge is preserved, yes. Current, it will split. That's why we talk about the adding up of currents at junction. Yeah, so the definition is this. The concept is conservation of charge. So you should write charge on the second one. This would be a independent mark. All right, so we come on to this circuit, a battery of electromotive force, e.m.f, 8 volts, very good. And internal resistance, 2 ohms. This is the annoying thing that will cause us to lose some energy later. Connected to a resistor, X, wire Y. Okay, what do they want us to find here? So they gave us a resistance. The current in the battery is 2.5 amps. 2.5 going in and coming out. Calculate the thermal energy dissipated in the battery in the time of 5 minutes. Dissipated in the battery means who is the one causing thermal energy to be lost? This one? This one? Oh, this is outside battery. And you look inside the battery. We have this resistance. The battery's internal resistance, which we usually don't like, but what to do is there. So this battery is going to get hot because of this resistance. So you want to find thermal energy. We call that Q or sometimes E. But end of the day, you will want to use this equation for energy. E equals to VIT. Let's start off with this. But hang on a second. If we use this, what V would we use though? This is energy dissipated. Because when we use this equation, we need to know very carefully what are we plugging in here. So current through the battery is still 2.5. That one is straightforward. But V, we're looking at dissipated. So energy dissipated. Who caused energy to be lost? It's actually the lost volts. This one. V lost. But we don't know that. So we're like, we total the V loss. You can calculate it, but actually that's in the second part of the question. So maybe what you could do is use a different version. We don't know V. It's okay. We use a different variation of this equation. So if I substitute V equals to IR inside this, I want to get rid of the V. So this will become I square R times T. Yeah, I sub in V equals to IR. So right here, V equals to IR. Throw inside here. This one we have enough information. So now we know energy got lost because of a current flowing through this resistance. Oh, so maybe you should put this as small r. It's got a small r. All right, let's see. So we plug in the values in here. We will have 2.5 times 2.0 times, how long is this battery running for? Oh, 5 minutes. Minutes. Please remember to convert your minutes. 5 minutes times 60 seconds per minute. This one more correct. Okay, so if you plug in all this, you will find a total dissipated energy of about 3750 joules, which can be round off to 3800. Okay, so first mark is whatever version of the electrical energy equation you use, whichever one, as long as you write it out or show that you knew that equation, that's one. You can have 1 mark there. And the other mark is if you have your 3750, this is in the 3SF version, or you rounded it off to 2SF, also okay. Yeah. So also okay. 3750, 3800, also okay. So for those of you who use VIT and then you go and plug 8 times 2.5 times, what's it called? 5 minutes. Okay. If you use 8 as your V, you are not calculating the energy dissipated. You're calculating the energy produced. We want energy dissipated. So we need to find lost volts and plug inside here. This should be lost volts, not the 8 volt. That is EMF. EMF. Okay, let's move on to the next part. So now you are talking about terminal potential difference. What's terminal potential difference again? Yeah, this one is, remember we talked about battery internal resistance. If you take a real life battery and you say, I want to measure the voltage across this battery, and you put it like that. On the battery, they write there 9 volts. But when you measure, and especially when it's connected to a circuit, okay, connect to a circuit, you will realize that you don't get 9 volts. Maybe you get 8.8 volts. Why? Why do I have lost volts? That's because of internal resistance. So your battery does get hot after running a while because of lost volts. So what they say their EMF is, the sticker on the battery, may not be the same as what you measure when the battery is running in the circuit. So what we need to find here is if you want to find the terminal potential difference, you need to know EMF, okay, so whatever EMF there is, minus whatever you have lost due to internal resistance. So we got to go up to our diagram here and see. How do we find, is EMF given to us? Yes, it is 8 volts. Internal resistance is given. We don't know the lost volts, so we can try to find it a bit. So EMF is 8 minus lost volts. To find lost volts, this one, you can use V equals to IR. VIR. Yes, VIR. But make sure you know which V. This is lost volts, current, and small internal resistance. So we need to take the current, 2.5. Let's write it down here. Times internal resistance, 2.0. Okay, so right there, 2.0. Actually, how much is their value? Let me calculate and see. 2.5 times 2. Oh, 5 volts. What am I doing? 5 volts. So this lost volt we gone. We lost 5. 8 minus 5 is 3. So we can say, okay, you have 8, you lose 5. So at the end of the day, what you actually get out of this whole battery as a whole, and is given to the resistors outside, external circuit, this terminal potential difference is only a wimpy 3 volts. This is terminal potential difference. That will be down here, 3 volts. All right, so this is a mark your work. This one, final answer line cannot be 1SF other than uncertainties. So here, don't just write 3 volt. This one I can mark incorrect. You must have a 3.0 volt. Oh, if you forgot to put a 0.0, maybe write note to self. Hello, remember this one must be at least 2SF. Why? Because we are following what is given to us. Here is 2SF. Here is 2SF. All this is 2SF. So our final answer should follow. This is a calculated value. Follow the raw values used in your calculation. 2SF at least. You can put 3.00, but let's stick to 2. Okay, 1 mark only. So that's just for 3.0. Not much for working. So check and see if you manage to get that down. Or write a note to self. All right, let's go on to the next part. Determine the resistance Ry. Oh, how do we find resistance? Okay, we think and see what equation got resistance. Maybe the first thing that come to mind is R equals to rho L over A. Means this one can find resistance. Yeah, but we don't have length, we don't have area, nothing about the wire. So no. Then the other or the possible option is Ohm's law already, VIR. If you're finding resistance on Y, you need to figure out what is the current through Y and what is the potential difference across Y. Do we have all that information? We don't know R. Okay, we want to find R. Do we know current? Nope. This is current, IY. Potential difference? Oh, we do know potential difference. Because if the battery is supplying 3 volts here, then I can draw a loop and say, oh, so 3 volts will be supplied to wire Y. Because it's in a loop. You go up by 3 volts, then I have 3 volts to use. So yes, I know it's 3 volts potential difference, but that's it. Not much else that I know. So here is 3 volts. So I need the current if I want to use this method. This question got a few methods. Any tips on how I can find this current? Oh, here's a junction. If I can find what is this current, I can find IY. Let's see. So for the other resistor, I could say, hey, this one also get 3 volt. They are parallel. All is parallel with the battery, so everybody get 3 volt. I know V, I know R, I can find the I. That's a clue. Okay, let's try that out. Let's try that out for X. Let's find the I at X. Yeah, let's try that as our first clue. Need to unveil the secrets of the circuit. So V, Y equals to I, Y, R, Y. Let's use all these values here. So 3 equals to current to, wait, we don't know the current. Wait. IX. And the resistance, 15. So yeah, we'll take 3 divided by 15. That's a good guess. If you decide to guess that, we'll discover that this is 0.2 M. So here is 0.2 M. Aha, now we know already. You can find this IY. Into a junction is 2.5. Come out is 0.2 and something else. So based on Kirchhoff's law, what goes in must come out. So your IX plus IY should equal to 2.5. So you can say that IY is 2.5 minus 0.2. That's 2.3, I think. Yeah, 2.3 amps. So you can do a quick check. If this is 2.3, 2.3 plus 0.2 is 2.5. Okay, good. All the current into junction equals to out of junction. That's the Kirchhoff's first law that we just stated. up on this left corner. Okay, now we have figured a missing piece. We can calculate for the long wire. So we do the VIR again. But this time for Y. Okay. Did I write wrongly? Yeah. Ah, yeah, this is for X, my bad. This is X. So now we do everything for Y. We know Vy is 3 volts. Current, 2.3 amps. Resistance, don't know, but we can find it. This one, when we divide, we should get an Ry of 1.30 ohm. Ah, so this is the puzzle solving method. You need this, you don't have this, you go and find first. So try to solve, find the circuits. So here's a 3-mark question. The first one is if you got the 0.2 amps, either written in the diagram or written somewhere, 0.2 amp is current through X. Then you have the current through Y, 2.3 amps. And lastly, your 1.3 or 1.30 ohm. This is one method. The other method, let's write it out, is to use the total resistance in the circuit. So you see this resistance, this circuit here, I'm going to redraw it into something else. So you may have done this method, is also okay, can do. So let's say I simplify my battery and I say terminal potential difference is 3 volt. So 3 volt is kind of given to everybody else. We got one here and another resistor right here. This one, I have no idea what this Ry is, but I know this one up here is 15 ohm. And I know that the current flowing through this battery, total current, sometimes we call it, is 2.5 amp. Okay, that's it. So I move over this side already. So if you say it means I want to use total resistance, can. Total resistance equation. So the total with VIR first, R total equals to voltage, which is the e.m.f. Okay, so I'm going to change this up to e.m.f. E equals to IR. I can find the total resistance if I take 3 volts, so-called e.m.f. I simplify my battery a bit. Divide by 2.5 amp. And then the next step, I say, oh, I can combine these two resistance in parallel. So my total resistance, R total, is 1 over 15 plus 1 over Ry, and I inverse the whole thing. This is the formula to combine resistance in parallel, remember? So then I can sub in, oh, 3.5, 3 over 2.5 is this. So I write that here. 3 over 2.5. And from here, I can rearrange to find Ry. So this is a possible other method you can use. Which one do you prefer? It's really up to you, but I would recommend you know how to use a few methods to find the same thing. Because then you can check answer. You see you got something wrong here or there or not. Okay, so this is the E equals to IR method. Different forms, but same idea lah. Okay, let's write 1.3. Let's go to this part 3 and mark and see. Hopefully you got to at least write something. Just try to write something. A new wire has same length, less resistance. State 2 possible difference between wire Z and wire Y that would separately cause wire Z to have less resistance. Oh, so you think of wire as a property of itself can be calculated. I mean, you can calculate the resistance with rho L over A. So they said the length between these two wires is the same. So length is constant already. I kind of put a box to remind myself, oh, it's constant. So what could change though is the resistivity of the material. Is it copper? Is it iron? Is it steel? Or the cross-section area of the wire. There's a wire, got cross-section area. Comparing both wires. So what would cause it to have less resistance? So I can kind of check. If R decrease, what about this thing? This thing would have to decrease as well. That's one possible reason why they have different resistance. So let's say that. So you can say wire Z They say Y less resistance than Y ma. So wire Z has smaller resistivity. And that's related to material resistivity. Depends on the type of material it is made of. Another possible thing you could change to affect the resistance is area. So this area here. This is an inversely proportional relationship. So if you want resistance to decrease, you need a larger cross-section area. So that's the second possible difference between both. So you can say wire Z, if you want it to have a smaller resistance, it has probably or possibly has a larger cross-sectional area. Some of you may prefer to say, Miss, can I say diameter instead of cross-section area? Can? So this one, or diameter, or radius. Because at the end of the day, A equals to pi d squared over 4, or pi r squared, which is a circular cross-sectional area. Right, so any of these 2 points is a good mention. Larger cross-sectional area or radial diameter. Okay. Diameter or radius. Or smaller resistivity. That's another possible one. Okay, so this is based on the idea that R is proportional to resistivity and also R is proportional to 1 over A. Or R proportional to 1 over D squared. Okay, last part. So now you actually take this wire Z and replace wire Y in the circuit. Where's our circuit? Here we go. So wire here you take out, put in a new wire that has less resistance. Okay. So what are we supposed to do now? By considering the current in the battery, state and explain the effect. Ooh, 2 things now. State, explain. What are we explaining? Effect of changing the wire on total power produced by the battery. So when you change the wire, how did the power produced by battery change? How did it change and why do you say so? So that's a state and explain combo together for us. We need to answer. So before we start this, while we're still thinking about this, I'm going to redraw the circuit real quick so that we can take a look at what is happening here. So we have the internal resistance. Kind of draw that inside the battery. So I put this dotted line. Then we have first resistor, second resistor, or wire. Okay, I will draw this as wire. In real life, actually, all wires have resistance. It's just that to make our lives a bit easier, we consider them in these questions. We don't say the wire have resistance unless they specifically say so. Okay, so we have here total power produced that we're trying to find. How are we gonna start? Here are some hints to underline. They say by considering the current in the battery. So maybe that's a hint. How does the current in the battery change when the resistance of this wire decreases? Because we replace with a new wire Z ma. Wire Z has less resistance. That's one tip. Okay, so maybe we can think of that. And also, what power are they actually asking for? They want total power produced by the battery. We know power is P equals to IV or I square R. But the question is, what V do we use here? Remember the question, you cannot simply use the V. You know which V we are using. Current we know is the same passing through. Do we use loss volts? Do we use e.m.f? Or do we use, what's the other one? Terminal potential difference. There's so many V's. Think about produce. Which of these V voltage is the one that produces energy in the first place? That will be your hint. So let's change this up. Power produced in the battery. This will be I times some V that we don't know what that is. Let's write here first. So actually, if you want to know what is power produced, if you have a battery cell, the source of its energy is actually the chemical reaction inside our tiny little battery. Okay, so you can't see my battery. Tiny battery. Okay, so our tiny little battery has some chemicals, and that is related to the e.m.f. actually. So there's many type of power. If we use e.m.f, this is power produced. The sentence they will say power produced. This. If you want to use lost volts in your PIV equation, this is power dissipated. The language they will usually use, or power lost. If you use the terminal PD inside this equation, then this will be power supplied to external circuit. What actually is useful that the resistor down there can use. So power supplied to external circuit. In other words, it's the output of the battery. Input is this one. Produce power by chemical means. So 3 different power, make sure you know which power we are talking about. So actually this one we're going to take P equals to I times E, e.m.f. Because we want to find produced. So so with that in mind, we know what power we're looking for. Not the lost volts, that's power dissipated. Not power supplied, that's a different power. We're going to find power produced. So let's talk about the current. So what happens when we change this resistance? Let's start off with that. You can say when wire Z is replaced, total circuit resistance will decrease. So we can write that down first. Total circuit resistance is lesser than before. Total circuit resistance decreases. Oh, that means when there's less total resistance, the current through the battery will increase. So we can say, so current, we don't say total current now, we say current through the battery before it's split up into all the branches here. Current through battery increases. Okay, last step. So what does that mean for our power produced? Current increase. e.m.f, they didn't say anything, no chemical change, so we assume this e.m.f is a constant. If it's 9 volts, it's 9 volts, whatever the battery is. So if current increased already, that means there's more power going to be produced by the battery. So we say hence, or we say since power produced can be calculated by E times I, IE, whichever one, IE, so power produced increases, power produced by battery increase. So these are the 2 main ideas. One for this, one for this. Let's give it a B1 and a B1. So check your working. Marking, do you manage to hit these 2 points? And remember, there's 3 types of power, at least for the battery itself. And you could find the efficiency of the battery, by the way. Ooh, some past year do ask about efficiency. Then you have to take the power output over the power input. In other words, this is what is actually useful. Actually used in circuit. Okay, thanks to the terminal potential difference. Input is what actually produced in the chemical cell. Then it's not 100% efficiency when you have lost volts, because you lose it, the wasted energy you just throw into the air. Okay.